This is the second part of curve sketching, and that is interpreting and sketching derivative graphs. Um, so what we're going to do is we're going to sketch the first derivative and the second derivative graphs from the original function graph, the original position graph. So just to give a an anchor for how we're so that we can see why the derivative graphs look the way that they do. They're going to look very different from the original position graphs. And basically what's going to happen is um, originally our position graph, the y values represent physical location of these for these x values. But for our derivative graphs, the y value will now represent slope and no longer position. And what we can do first is let's create a um, let's create a table of values, a t-chart, t-table for a value, for an x value and the slope of the tangent line at that point on the curve. But we're just going to um, just do a rough estimate based off of what we can see. So we're just going to look at a graph and determine what we think is its slope. If we see a steep slope, then either it'll be a larger positive or larger negative value. But if we see a gradual slope, then we want that value to be closer to 0. So at -4, so I'm going to just list out x values from -4 all the way to +3. Um, and we're going to just see what we can just make a guesstimate as to what the slope is at that point. So here at -4 we see that this is a rather steep slope, so I'm going to say that the slope is probably around a larger positive value greater than 1, so I say +5. At -3 we see that this is a slope of 0. At -2 we see that this is a negative slope here, so negative slope probably not as steep as this, but we'll just say this is -4. You could say -3, or you could say -2. Okay, we're just making an estimate here. At -1, we see that the slope of the graph is 0. At 0, we see that the slope is positive, so maybe 1/2, 1 or 2. I'm going to say 2, but again, we're just making some estimates here. At 1, we see the slope of this graph is 0. At 2, we see the slope is maybe -1. But then at 3, we see the slope, the graph is getting steeper in the negative direction, so I'll say -4. But maybe it's a little bit less than that. Now, based off of these ordered pairs, let's create this graph. So if we create this graph, and I put this up here, it's not very smooth, but we see the basic shape of this graph, right? -4, 5, -3, 0, -2, -4. So if you look at your derivative graph, it's a lot different than your position graph, right? Because the y values represent something different than this y value here. Okay, so we're going to talk about method that we're going to take to go from this graph to this graph without having to resort to look at each ordered pair every time through. Okay, so the steps that we're going to take is we're going to look at our position graph, and we're going to determine our critical points, and from our critical points we're going to create a sign line for slope. Now we know our critical points will be where we have relative extrema or where slope is 0. So we see that our position graph, our slope is 0, will be at -3, at -1. I know it's a little bit off, but we'll say it's -1, and at 1. So we put those on a sign line. And then we just basically look at the graph, right? If the graph is rising, then obviously it's positive slope. If it's falling, then we know it's negative slope, positive slope, negative slope. So we put all this on the sign line. So now we're going to use this information to create our first derivative graph. Okay, and with the first derivative graph, again, the y values represent something different now. Y values now represent slope. So I'm going to make a bracket here to indicate anything that sits above the x-axis would be where we have positive slope, where the original graph will have positive slope. Um, any points that sits on the x-axis will be where the slope is 0. Anywhere that the graph is below the x-axis indicate where we have negative slope. Okay. So first thing we do is we plot these points onto the sign line because that's where slope is 0. So that's the easy part. So now the next part, we want the graph to be continuous because our function is continuous and our f prime will also be continuous. Okay. Now we want this first portion to have a positive slope. Now positive slope, that means we want this portion to sit above the x-axis and we want the graph to connect through these points. So first thing, we're going to have a graph that goes down to -3. Okay. So this is above the x-axis, so that's exactly what we have. We have this portion to the left of -3 to be above the x-axis. Between -3 and -1, we want the graph to be below the x-axis to indicate that this graph has negative slope. So then we just have the graph drop down towards negative, but we want it to come back up because we want this graph to connect through these 3 points. So it's going to come back up to 0. And then once we're there, we see that the graph is going to increase slope again. So we want this portion to be above the x-axis, but it's going to eventually reach a slope of 0. So we want it to go back down to 0. And that will occur at 1. And then to the right of 1, we want the graph to have negative slope, so we want this portion to be below the x-axis, so that's what we have. Now this may seem confusing, but if you look at what we created by looking at order pairs for slope, we see that we get something that's very similar. Okay, so it's going to take some time to maybe wrap your head around why the graph looked the way that it does. But we have to keep thinking about the fact that these points no longer represent position. These points now represent the specific slope of the tangent line to the graph. So now we are going to take this. We've created the first derivative graph. So now we're going to create the second derivative graph that represents where the graph is concave up and where the graph is concave down, as well as points of inflection. Now, points of inflection is going to occur where the graph changes concavity from down to up, from concave down to concave up, so that transition point, and then from that concave up to concave down, again, that transition point. Now, the transition point is a little, it's not very clear where that transition point is. We know somewhere in this region, and here we know somewhere in this region. So if you're looking at the original function graph, you're going to have to be told more information. Either a function where you can actually find the second derivative and find the point of inflection, or they'll have to tell you where the points of inflection are. So in this case, I'm going to tell you that the points of inflection will occur at -2 and at 0. Okay. So now we know that at -2 and at 0 will be where our critical points are, because these are the transition points, the points of inflection. And then we can look at this graph to tell that this is obviously concave down, followed by concave up, followed by concave down. So that's exactly what we're going to create with our second derivative sign line. -2 and 0 are critical points. We see that the graph has that shape of concave down, followed by concave up, followed by concave down. So now we're going to take this information and we're going to sketch it onto our second derivative graph. So now our second derivative graph, again, the y value represents something different. It's not position, it's not slope. The y value now represents concavity. So anything above the x-axis represents concave up. Anywhere on the x-axis represents where we have critical points, where second derivative is 0. Anywhere the graph is below the axis will represent concave down. So first thing we do is we plot these two ordered pairs, -2 and 0. And then we look to the left of -2. We obviously want the graph that's below the axis, because we want this portion to, this is going to represent concave down, so we want the y values to be below the x-axis. But we want the graph to connect through these points. So we're going to have the graph increase through that point. Between -2 and 0, we have concave up. So the graph to be above the x-axis, but eventually want to come back down to 0 because points of inflection will be at 0. So we want the graph to increase and then fall back down to 0, and finally this portion to be below the x-axis. Now notice how the shapes of the graph changes. So here we have something that has 1, 2, 3, 4 direction changes. So this is a quartic function, right? X to the fourth, maybe negative x to the fourth. The degree is to the fourth power. Now if you find the derivative of x to the fourth, it'll come back down to a cubic function, and that's exactly what the derivative we have, right? The derivative function now is a cubic. And if we find the derivative once again, x cubed becomes 3x squared, and if we find the derivative of a cubic, we're going to come back down to a quadratic function, and that's exactly what we have here with the second derivative. We have a quadratic function that is opening down. Okay, so the same idea here with number 2. What I did here was I created, this is not necessary, but just to show how the derivative graph is created. We're basically listing out not the positions, but the slopes at each of these x values. And if you graph this, you're going to have this this graph that will be a cubic. Okay, so much in the same way, we can create a sine line for slope by picking out points where the slope is 0. So slope is 0 at -2, at 0, and at 2. So we put those on a sine line. The next thing we do is determine the slope of this graph. So negative slope followed by a positive slope, followed by a negative slope, followed by a positive slope. Now we can convert this to f prime graph. Again, anything above the x-axis represents positive slope. Anything on the x-axis is slope of 0. Anything below the x-axis is a negative slope. First thing we do is we put these points onto the sine line, onto the graph, f prime graph. And we just have to know that we want this graph to be a smooth curve through these points. Okay, so we're going to start below the x-axis. Next, we want the graph to be above the x-axis. Next, we want the graph to be below because we see the negative slope. Come back to slope of 0, and finally increase above the x-axis. And I'm telling you're being told that the points of inflection for the original graph will be at -1 and at 1. So we see the graph is going to be concave up, followed by concave down, followed by concave up. So we put those information onto the sine line for our concavity slope, our concavity sine line, and then we translate that onto our graph. We put our critical points onto the sine line, onto the graph. We have this portion to be above the x-axis. We have this portion to be concave down, so that sits below the x-axis. And finally, we have a portion that's concave up, so that's above the x-axis. And we want the graph to be continuous all the way throughout.